what I want to show you today is that in the world of radar, there is no such thing as day and night anymore. I want to show you that radars as active sensors that are transmitting their own energy, their own light source. It doesn't matter what time of the day it is. You can make the same measurements with the same quality at any time and at any point in the world, on this globe, and on other planets. So that's one of the points I want to bring across. So you may not know it, but pretty much every one of you has somewhere in his collection of gadgets an instrument that is using radar. Or every one of your lives was touched by radar in one way or the other in the past. If you ever flew in an airplane and you had an overnight landing, what brought your airplane in safely into the airport was a radar system. It was some radar guide path that helped you land safely. If you have one of the new cars that has one of these backup alarms, if you back up and it starts beeping when you get too close to something, that's a radar system that is warning you that you're about to hit somebody or something. If you ever watch the weather forecast, a lot of the weather forecasting is done using radar sensors. So radars are really, I wouldn't say running your life, but they are a huge portion of your day-to-day life. Now, I want to talk about a slightly different part of the radar world. I want to talk about something that we call remote sensing. And what this really is we take radars and we form images from using radar systems, and we use that to study our planet. So in this talk, I want to start out with sort of defining what radar is, talk a little bit about defining what remote sensing is, talk about how remote sensing and especially radar remote sensing had developed, and then show you bunches of examples of what radar remote sensing can do for you, especially here in Alaska. So I'm hoping that it's going to be interesting. So my fairly narrow-minded definition of remote sensing is sort of the science of understanding and measuring the world using images. So I'm interested in geoscience questions. So I'm seeing remote sensing as a tool for me to understand the planet. So to understand how it changes and to understand its dangers and to monitor it at all times. And we can do that with various different means. Nowadays, we mostly do this using satellites. So we have satellites out around the planet. And I want to show you today that especially radar satellites can help us understand hazards and manage hazards. For instance, oil spill type hazards or flooding events. We can monitor those really well with radar. I want to show you that we can monitor the climate if we want. We can look at ice sheets and glaciers and how they change. We can look at sea ice, which in Alaska is important for many reasons. And we can look at geophysics. We can try to understand how earthquakes work, and we can try to understand how volcanoes behave. So all of these things I want to show to you today. Now remote sensing as such is pretty old. Remote sensing as a discipline has started already early in the 19th century. Actually, essentially with the first image ever taken by anybody in the world, that was the first remotely sensed data set that we ever had. And the first image was actually was acquired by a Frenchman from basically his window. This is the first ever photograph in the world, and aren't you glad that we have improved quality since then? So this was taken by a guy called Joseph Niepce. That's probably horribly mispronounced. I'm not sure how to pronounce French. So anyway, that's how this name is spelled at least. And in 1827, he had built the first primitive camera and had captured the first image. This image took an exposure time of about 8 hours. So just to let you know how ill-equipped they were at the time. So from there on, we developed first cameras. Cameras were developed further such that you can take images in shorter time spans. So you could put cameras in places where they didn't require to be stable for so much time. So this was put on a roof. This is a road in Paris, and that's the first remote sensing experiment because they put this camera on the roof and took images throughout the year of this road to sort of see the seasons and how things changed, how nature changed on this road. So the first primitive remote sensing experience. And then in the 1860s, we started taking remote sensing up in the air. So we started doing real observation from up above, initially using simple things like balloons and kites. So one guy that was pretty famous at the time was a guy that called himself Nader. He was also a French guy, and he used his balloon to map and cartograph sections of Paris, sort of to figure out where all the buildings and who is living where and so on. And the first geoscience application came by accident. It was really run by an American inventor called George Lawrence, who invented this camera that he could put on a set of kites. He had like a set of 3 or 4 kites that stabilized this camera. It was a pretty nifty thing. And it happened that after he built this camera, there was a huge earthquake in San Francisco. And he used his camera to sort of take photographs that documented the damage that was happening during that earthquake. So that was the first time that we used it to look at hazards. So optical systems since then have developed quite a bit. So nowadays we have, most of you may have heard of Landsat as a satellite system that had been around for 20 or so years and is imaging the planet. But all of these systems have 2 huge drawbacks. It turns out that, if you probably know that, but about half of your day on average is dark. So at night you can't take optical images. Optical images carry not that much information anymore at night. This is a Landsat composite of sort of the western United States at night, acquired by Landsat. So this is optical. So it's not free, it's not devoid of any information. You can see population centers, you sort of understand where people live. But in between, there's a lot of area where information just disappears. And by the way, if you don't know, you're here. So that's one problem that we're trying to overcome with radars. The other one is that even if we have daylight, it turns out that most of your time you actually spend underneath clouds. So even in the summers in Alaska, where we think that we're pretty cloud-free and it's pretty nice out here, it turns out that it actually isn't, if you look at statistically at the likelihood of there being clouds. So this is a global map that was also calculated from 20 years of satellite data. And what they did is they looked at every grid of the world and calculated what percentage of images carried clouds and what percentage was cloud-free. And they colored this map in cloud-like colors, so everything that's sort of whitish, like this stuff, means that it was under clouds for most of the time, and the things that are more bluish and dark, those were cloud-free most of the time. So large parts of the world are underneath clouds during the day, and then inaccessible at night with optical sensors. So that's an issue. I mean, if you think of a hazard situation, you know, an oil spill or an earthquake is not waiting for the sun to come up. So if you really want to be able to right away take a snapshot of what happened, you need a different type of sensor that can do that at any time of day. And that's what radar is doing for you. So to come to radar, so that was actually the first step of radar, was recognizing that there is an issue. The second step of radar was we had to develop some physics to really understand what radar is to begin with. And so really the beginning, if you want, for radar was happening in about the 1860s, when a guy called James Maxwell was discovering the theory of electromagnetism. So he was a physicist that was for the first time put a set of already existing laws together and understood that light and heat and electricity and magnetism are all one and the same thing. And they're all part of one and the same phenomenon that's called electromagnetism. And based on his theory, people could then come up with another kind of theory, which is the electromagnetic spectrum. So people then realize that what we think is visual is light is really only a very small part, is this fraction of all the energy that's out there, of all the information that's floating around. So at all other frequencies, there's information out there. There's energy coming in from the sun. It's reflected from objects. We could look at that and understand the surface. But we with our eyes are ignoring all of that information. So that's the first thing. There's way much more out there. That was the first sort of epiphany that people had. And then later on, people studied sunlight. So people went out there with spectrometers, and they analyzed how much energy comes from the sun at different frequencies. And they figured out over time that the atmosphere is actually blocking a lot of incoming light at a lot of frequencies. It turned out that for large parts of the spectrum, all of these sort of dark shaded areas, the energy cannot penetrate through the atmosphere. And there are a few areas, and one of them was the so-called radar window, which is here. Especially at the microwave range, at the radar wavelength range, the atmosphere is very, very transparent. And that's very important because this means we can we can transport energy and information at this frequency through the atmosphere, no matter whether there are clouds, whether there's haze, whether there's maybe an ash cloud, whatever kind of particles in between. The atmosphere is transparent at these wavelengths. So then people started thinking about, hey, what if I could harness microwave energy? What if I can build a system that can actually generate light at these frequencies and send it out into the world? Then I could transmit information. This was sort of the start of telecommunication in that sense. And I could also use it to find objects. So I could send that out. It might bounce off something and come back to me. And then I would be able to sense and find this object that was in the way. So that was the start of people thinking about radar. And so the first one that built a first radar transmitter was an Italian guy, Guillermo Marconi, in 1901. And it was proven that he managed to transmit a microwave signal from one place to over about 1 kilometer. He claimed also that he transmitted a microwave signal across the Atlantic, but apparently there are no witnesses, so that was never proven. He seemed to be, he apparently was a little bit of a show-off. But he built the first radar transmitter, and then there was a German guy called Christian Meyer, who got a patent for what he called an obstacle detector. And that was sort of the first quasi-radar. It was sending out microwave signals, and the idea was that the signal would travel out, would bounce off of something, and come back to you. And by measuring the distance, you can spot where this object was. So you can find it first, and you can locate it. It turned out that his construction that he had designed had some flaws, so it actually didn't work the way he wanted it to work. So if you're German like me, you would claim that Christian Meyer was the one that gave birth to radar. If you're from anywhere other than Germany, then you would say that this guy, Watson Watt, was the one that actually invented radar. And he actually has a patent that carries the name radar. So his patent was called radio detection and ranging, which he shortened to radar. So in that sense, okay, I give it to you. So he not only developed the idea, but he also developed the first system that worked. And again, we lose out as the Germans, because the system was planned to, was a defense system. At the time, the Germans were using the darkness of the night to run air raids against London. So they flew in on planes and bombed London. And so Watson Watt's idea was to build a set of these radar systems along the coast that can spot these planes when they come in, and not only spot them, but sort of track them over time and pre-warn London and pre-warn all the defense systems. And so he built a bunch of those along the coast and used them during the war. So it's the first time that it was also successfully implemented. So these are close to what I'm interested in, because they're able to locate an object and measure its distance, but they are not yet creating images. So what I'm interested in is forming images. So there was one more step, and it was an American in the end. So that's where America comes into play. A guy called Carl Wiley, who, out of all places, worked for Dunlop at the time. And he invented a processing concept that allows you to create very high-resolution images from radar sensors. And this concept is called SAR, and SAR stands for synthetic aperture radar. Not that important, but it allowed to make images from radar platforms. And pretty shortly afterwards, we put one of those SAR systems onto the first satellite. And we put that on a satellite called CSAT. And this is the first radar image that was ever recorded from space, and it was recorded by CSAT in 1978. So that's really, now we have reached a point where we have a system in space that doesn't worry about day or night anymore. So that's where I claim that the imaging radars are turning the night into day and make for a world without night. So that's the end of my pun. So don't worry about that anymore. And since then, we have built a whole bunch of those systems, and we put them into space, and essentially they all look like this. They're basically boxes. They have an antenna on the bottom. This is actually the radar antenna. And we put them in orbit, and so they're flying along. This is an example. This is the so-called TerraSAR sensor. This is a German sensor that's in space right now. I use TerraSAR because they put out the nicest videos. And so what you do is you point this thing slightly sideways, and you send out energy, and it travels to the ground, and it bounces off the ground, and when it comes back, you record it. And the objects that are closer to you, they come back a little earlier, so those you record first. And by sort of recording over time, you can form a nice two-dimensional image. And then when the system flies along, you just scan the ground while you fly along, and you create this very long strip of image along the orbit. And so that's really it. The principle is after you actually made it work, it's pretty simple. And you can run those systems in different modes. This is really what's shown here. You can run them such that they cover a very large area on ground at lower resolution, or you can build them such that they cover very small areas on ground at very, very high resolution. That's really the only difference. So you can put those things on the ground, like this one. This is one of those radar systems that you can just use on the ground. You can put them on an airplane if you want, or you can put them in space. Putting them in space has a huge advantage, because what you will see here is all you have to do is you have to put that satellite into an orbit a stable orbit around the planet. So you put them in space and have it rotate around the planet in a stable manner, and all the rest is done by the world itself. So when the satellite is rotating around, the Earth is rotating underneath it, and so every time the satellite passes over it, it sees a slightly different spot of the planet due to its rotation. And so over time, just by doing this, you cover the entire planet. So that's the really cool thing about satellites, is that you can cover the entire planet in a very short time. So this system needs about 11 days to cover the entire planet once. And then after 11 days, you run the same cycle again. So every 11 days, you get a full coverage and a repeat acquisition of every spot on the globe. So you can build nice time series and look at changes of the surface. And so this is what a radar image looks like, by the way. And I have to disappoint you, there's no color. So you're not colorblind, there's just no color in that image. All we can see is, basically what we see is we send this energy down, and we can see how much of that energy gets scattered back to us. So it's like a power image. So some points will scatter back a lot to us, and other points will scatter back very little. And in the end, it all has to do with what we mostly see is roughness. We can see how rough the surface is. In urban environments where you have like buildings that have corners and regular objects in it, those are usually very, very strong scatterers. Then objects that are sort of in the intermediate gray here, this is mostly different types of vegetation, forests, grassland, all of those have different types of backscatter, but they're all sort of in between, very bright and very dark. And then you have some objects that are very, very dark. These are usually very, very smooth objects. So the thing is, if you send the energy sort of down sideways, what we do in radar, and it hits the ground, if the ground is very smooth, it sort of acts like a mirror. So you send the energy down like this, and it gets scattered off in the other direction, and it just doesn't come back to you anymore. So everything that's very, very smooth will look very, very dark. And that's true a lot for water surfaces, which I will show you later is really one of the good things about radar, is that water mostly looks dark. And it's also true, for instance, this is an airport here. You see all these runways. So you kind of quality control for runway design. If they're nice and smooth, then they will be very dark in the radar image. And so those images we can take a lot. Every sensor is taking them every so and so many days, like 11 days, for instance. And then we have a whole bunch of sensors that are doing this. So in the past, we had a bunch of legacy systems that are not in space anymore, or are still in space but kaput. So the first one ever was CSAT, was an American-based system that sort of paved the way. And since then, we had European systems that operated for a very long time. We had a Canadian system that operated for almost 20 years, and a Japanese system. And currently, we have a set of a Canadian, a set of German, and a set of Italian systems out there. But so when we are currently what we are calling entering the golden age of radar, because starting this year, we have a whole fleet of radar systems that go into space. I only mentioned a few of them here, not all of them. So in the next 2 to 3 months, we'll have a Japanese system go up into space. We also will have a European system about the same time being launched. The Argentinians will launch a system next year, and then there's an American and also another European coming up in the near future. So we'll have lots of data to work with. Okay, so for now, all I told you is that we can make images, but I haven't told you at all why this is useful. So I want to show you a few things that we can do, pretty simple things, but pretty powerful things for places like Alaska. So one of the things that you know about and is a hazard in Alaska and a problem in Alaska are volcanoes. So obviously, if you live near a volcano, then lahar flows, lava flows, ashfall are an issue for you. Even if you, was anybody in Anchorage when Redoubt erupted in 2008? Nobody? Oh, one person back there. There was ashfall in Anchorage. So for at least a period of time, life in Anchorage sort of died down. So it's a hazard also on the regional scale. And on large scale also, because sometimes air traffic routes, like airplane routes, go across volcanoes. So if volcanoes erupt, these air traffic routes have to be shut down for security reasons. So it is an important topic. So one thing I wanted to show you, so one of the more active volcanoes in Alaska is Mount Cleveland. And I have a few volcano guys back there, so if I say something stupid, please let me know. So this is Mount Cleveland here in the Aleutian chain, so it's located about out here. And it had a little bit of an agitated period in 2011, where from about August to about November, I think, there was increased seismicity, and there was some reports from airline pilots that there were steam clouds on the volcano. So at the time, the Alaska Volcano Observatory jumped into action, and they wanted to monitor and make sure that there's no larger scale hazards happening. The problem was that for this time frame, there was hardly any useful data. So mostly they rely on optical and thermal remote sensing data sets, and because of prevalent clouds in the region, it was very hard to get anything useful over that volcano. So one of the few useful data sets we had was a series of radar images from one of those higher resolution radar sensors, and they are shown here. So this is a side view of this volcano. Starting somewhere in August 2011, and I think until November 2011. So this is the main edifice of the volcano. This is the crater of the volcano. And then you see this little tongue start to stick out here. So you see in the beginning it's really small, and then it's growing over time. And this is what's called a dome. So what's happened was that magma was rising from through the volcano and was oozing out on top, and was building sort of this dome-like feature. So that was really one of the few direct evidence, one of the few pieces of direct evidence that there was activity going on in this volcano. And it's very important too, because those domes are tricky. If this dome grows and grows with time, and it sort of becomes steeper on the side, it may collapse. It may become unstable and collapse. And you may have an effect like pulling a cork out of a champagne bottle, and you may lead into an eruption. So it's important hazard information. Another thing I wanted to show you here is one thing that radar is really good at is because radar is carrying basically its own sun, its own illumination source. we have complete control over the data we acquire. So we send out the same energy every time we take a picture. If we do that from the exact same place, so every so and so many days we come back to the exact same place, we send out the same amount of energy, the two images we acquire would look perfectly the same unless the surface has changed. So we don't have to worry about shadows. We don't have to worry about, today the sun was, we had a different time of the year, so the sun was lower. Because we carry everything ourselves, we have our own flash, basically. Every image will look exactly the same unless the surface has changed. And you can see that here quite nicely. It's like the images look very similar, and you can very easily spot the thing that actually changed up here. It's a very nice feature of radar. And I want to show you another one of those. We can use same process for looking at ice, at sea ice. So sea ice is very important for Alaska. If you live out here along the coast, you use in the winter land-fast ice to travel. You use it for fishing, to get to your fishing grounds. Oil companies are using land-fast ice to travel out to their oil rigs and transport goods out there. So it's knowing sort of the stability of ice is very important. On the long term, if we have an Arctic that is opening, if the ice is going away more and more, we want to know how much ice is left, where the ice is coming from, how large icebergs are, because if somebody is planning to build an oil rig out here, we want to make sure that it's safe. So these kind of things, for all of these kind of questions, we need lots of data. We need to look at distributions of ice and changes of ice. And radar can do this. So this is an example. This is the Alaska North Slope. Barrow is about here. So this is North Slope here. Everything out there is sea ice. So first you see that sea ice comes in various shades of gray in radar data. So you have these like brighter spots. What do you think these are? Huh? That's older ice, right? This is sort of rugged on the surface, older, thicker, multi-year type ice. While the darker pieces here are smoother and younger ice. So that's immediately important if you are an icebreaker captain and you wanna get from here to up here. And you want to find a route that is safe. You want to be maneuvering through areas where the ice is thin. And this kind of data can show you that. And then you can go ahead and, if you're a scientist, you can look at the entire ice season. So this is what's shown here. This is from 1998 in the fall to 1999 in the spring. And so let me do that again. You see sort of initially the dark stuff, the ocean is kind of ice-free, then you see slushy ice move in, then the ice sort of gets thicker over time. You see these brighter features of multi-year ice moving in. You see areas along the coast where the ice suddenly is stagnant. It doesn't move anymore. This is the landfast ice. So you can see all of these things develop over time. You can see how fast ice is moving, and you can see at the end how long the ice season was. So because you get these reliable images every so and so many days, you can analyze these kinds of things nicely. And it doesn't have to be sea ice. You can do that for land ice also. This is not Alaska in this case. This is the Antarctic. This is an image every 11 days from the same spot acquired of this glacier, Drygalski Glacier in the Antarctic. And when you look at the frames put back to back, you see how the ice is moving. Very cool, actually. You see how these crevasses are slowly drifting downwards. You can see it especially here. You can see how ice is calving and it's then moving away over time and is sort of pushed out into the ocean. You see this like darkening and brightening. This is a weather effect. What's happening in the dark images, it's getting warm. So there was a warm period. And the ice on the surface, the snow on the surface started to melt. So you had a film of water on the surface that then made this a smooth scatterer, and we had this like smooth scattering effect, and the ice darkened down. So a lot of information that's in here. And again, if you look at the rocks, those are extremely stable. Those didn't change over time, so they look the same in every one of those images. And of course, one of the most important things is safety, is looking at disasters, looking at disaster management, helping people help other people, basically. And that's another stronghold of radar. So imagine you have a flooding event like this. When there is flooding, it's usually there's lots of rain, there are heavy clouds, so optical systems are really difficult to sort of acquire any kind of useful data. Radar data, on the other hand, can do that quite easily because we can penetrate through that cloud. And you will see that this satellite is slicing through clouds like a knife when you look at the animation. It's kind of a little clunky. But so there are two things that we are taking advantage of here. Is one that the signal can go through clouds unaffected, as you see how we slice through. and the other thing is, as I told you earlier, water looks very specific in radar images. It's very dark. So we can very easily and automatically find all the flooded areas right away. So there's a flood, we take an image, we can map those areas right away. We can put those areas onto cartographic maps, overlay them with known information, and we can see, oh, look here, we have lots of houses that are underwater. We have an access route that is flooded, so you can't go through here. So you can give that to an emergency response person, and they can say, oh, instead I have to sort of travel in from this route, and there are lots of people that are in big trouble. So this kind of information you can create reliably, independent of weather conditions. On a smaller scale, we had actually, I'm not sure, is Mark here, Mark Fonstock? Oh, here. This guy back there is owning one of these sensors. So it's not mine, although I would like to have it. This is a ground-based radar system. This is doing the same thing, essentially, as what we have in space, just on a smaller, not much cheaper scale. And so Mark, I think by accident, put out in 2013 in May one of those systems along the Tanana River on the porch of some person whose name he couldn't remember. I'm not sure if you remember it now. So we put it out there on the porch, and it looked over the Tanana River at the time. And so just to show you, so this is the system. So one of these antennas is the transmit antenna, so it's sending out microwave signals. Not right now. And those two are receiving channels, so they would receive the reflected signals. And what you do is you rotate that thing back and forth, and it would scan off a certain area, and you can make an image. And so when you do that, so what they did is they looked over the Tanana during the breakup season, and I show you the image first, and then we go back through it. You already know this dark stuff is the river. This is water. This here is an ice jam that developed. And all of these black areas here, those were flooded by the water level rising. So when you look at that series of images, you can see, how this ice jam is forming, and you can see how the water level rises, and then you can see the ice jam let go at the end of it. So it's kind of nice. So imagine that you have that in a real, this is of course not a really serious ice jam, but if you would have that at a really serious place, you could acquire lots of information right away. Say this is a jam that is causing serious blockage, and you live like 2 miles upstream. If this would be detected right away, people can be warned and can move away until the flood travels upstream. So you see here how the water is sort of coming into here, and then it lets go. And so if you look through that frame by frame, you can understand, okay, what caused that ice jam? There's a bunch of ice pieces that come down together and block the river down here, and then everything else piles up behind it. And so not only can you use it in emergency response, you can also use that to sort of understand how this actually works, how the physics of these ice jams happens, and what makes ice jams go away. Okay, so far, technically, this was relatively simple. We take repeated images and just compare them. There's a little bit of a kink to radar. So radar does actually do two things. One of them is that it acquires those images that I had shown you before. But another thing that it does, is it measures a second parameter that we call the phase. And what phase really means, the phase is really a measurement of distance. So with every image that we acquire, we measure the distance between the satellite and basically every point in the image. So to every one of those points, we measure the distance. So if we do this again, so the satellite has acquired one image, comes back 11 days later, and stops at the same spot, and takes another image. So, and again, we measure that distance. So technically, this distance should be the same. You know, if we're at the same spot and we look at the same ground, the distance in both images should be the same. So the phase measurement should be identical. In reality, it often is not. And one reason of that is that sometimes the surface is moving. So you could think of an a glacier moving down the slope. So the same surface has actually moved a little bit, and we can measure that motion using the phase. And the phase measurement is at the scale of the wavelength. So the systems we're using have wavelengths in a centimeter scale, about 5 centimeters. So by measuring the phase, we can actually measure motion that is smaller than that 5 centimeter scale. So from a distance of 800 kilometers, we can tell you, in most cases at least, whether or not this ground has moved in a centimeter type scale. So it's a pretty incredible measurement if you think about it. And we can use that for lots of really cool things. Mostly sciencey, but something that may lead to more hands-on application down the road. One of the things that we're doing a lot with it is we look at volcanoes. It turns out that volcanoes actually, when they go through an eruption cycle, they are inflating and deflating. Not all volcanoes, but many volcanoes do that. So when before an eruption, there's sort of magma flowing into the magma chamber, underneath the volcano, there's pressure created in the subsurface, which is then transferred upwards, and it's leading to like a balloon-like uplift of the surface, like you blow up a balloon. And this is of course way exaggerated here. So this happens before the eruption, and then when we erupt, this pressure goes away, and the volcano goes back down. And this is really something very subtle. It's centimeter scale. It's just a few centimeters per year. But using this method, we can actually measure that. And so this is a measurement made by a colleague of mine, Zhonglu, that now is at the Southern Methodist University in Texas. He used that to look at Mount Pulik, for instance, here in the southeast of Alaska. So what you see here, every ring of constant color, like this, if you follow this blue ring around, every point on this ring has risen and uplifted the same amount. So it's like an isoline of uplift, basically. And so, and from one blue ring to the next blue ring, the difference in uplift between those is only 2.5 centimeters. So if that one didn't uplift at all, this one had uplifted by 2.5 centimeters. So it's, oh, excuse me, blow out your ears. So if you count up these rings, you can come up with how much uplift there was in the center, and in this case it was 17 centimeters. So it's really small, but it's also very, very evident. You can see that very clearly here in the image. And in this case, so sometimes this uplift causes an eruption, but not always. In this case it didn't, I think. No, it didn't. And but at the very least, you can use this to understand what's happening underneath the volcano. You can use that to figure out where was the magma source, how deep was it, how much magma was intruding, all of these kinds of parameters you can estimate from these kind of measurements. And you can then further down the road, you understand your volcano just a little bit better. And this Zhonglu I talked about before from the Southern Methodist University, he looked at every single volcano in the entire Aleutian chain and saw and checked for whether or not they are deforming. So he used the same method and had looked at every volcano. And every one of those that he's shown up here, those are actually deforming. You see these fringes. I'm not sure if you can see that, but you see these color circles maybe. So there's lots of activity going on in the Aleutian chain as radar shows. So just before I'm not going to try to stretch your attention too much, but I want to quickly go large scale. So as I said, you can do that for the entire planet. And there are people, this is a group out of the University of California, Irvine, that had took it upon themselves to map the entire Antarctic. So they used thousands and thousands of images to create this first ever image mosaic of the Antarctic. So this is the entire Antarctic, and they measured both, they took the images and put them together, but they also looked at the phase measurement to measure motion. And so there's probably a little bit too much information on here, but if you look at the right-hand side, this is the surface velocity of all of those glaciers for the entire continent of the Antarctic, all measured from using radar. And so here, this sort of reddish, brownish area is sort of the ice divide of the Antarctic. So at these spots, you have snow accumulation from sort of crystallization of snow and snowfall. And from there, the ice is sort of drifting down the slope to the coasts in both directions. And then it's sort of speeding up slowly, and then it's reaching those channels. And these are the so-called outlet glaciers through which most of the ice gets transported into the ocean. So there are very few of those outlets. And through those outlets, ice is flowing very, very fast. So up to tens of meters per day, or 100 meters per day, you can sit there and watch your glacier put thousands and thousands of tons of ice into the ocean. Very impressive. And then go back very small scale to get the scaling all the way through. We can also use that to look at individual buildings. If we use very high resolution images, we can look at elements of buildings and sort of try to understand if they move over time. And so this is one of a PhD student, a former PhD student of mine from Munich that did this work for his thesis. And what he did is he looked at Berlin, at the city of Berlin in Germany. And this is the central railway station in Berlin, which is it's sort of built out of metal and glass. And what happens is, through the seasons, with changes of temperature, the building is expanding. So what you see here is sort of the seasonally expansion and contraction of the building. And don't be worried, it looks kind of severe, but it's plus minus 1 centimeter, so it's not that dramatic after all. But you can use that to sort of understand, did I construct my building right? Is there any flaws in the way the building is designed? In fact, this piece here is a bridge. So this is another building, and there's a railroad bridge across over. I think there's a road underneath. And what's happening here is that these usually bridges have margins on the side, you may know. So if they expand in the summer, there should be enough margin to expand sideways. And for this bridge, those margins were too narrow. So instead of expanding sideways, the bridge is trying to do that, and it's then starting to bulge up. And it's not a lot. Again, it's a centimeter. So it's probably not a critical design flaw, but it's still a design flaw that you can find.
T-minus 15
seconds. So at the very end, I want to go back and I want to sort of tell you that while we can do that for the planets, actually the whole story started with other planets.
5, 4, 3, 2, 1. Main engine start. 0 and
so the whole usage of radar was way heavier in space exploration and in planetary exploration than it was in Earth-based exploration for a long time. So the first really heavily used systems were ones that were traveling out to other planets to observe them. And nowadays there's a whole fleet of radars out there in space observing all kinds of moons and planets in the solar system. And actually, while this is actually a Mars mission, I wanted to show Magellan, which was a Venus mission, but there's no video of Magellan launching. It's too long ago. But even this one has a radar on it. It was very important. When they landed do you remember the landing of that rover? When they landed this rover, they let it down on cables and stuff. It was really dramatic. The guidance of the entire system was done by a radar. So we claim radar is important. But what I really want to focus on about planets is Venus at the very end. And I will tell you why. First of all, there's a scientific reason for it. Venus is interesting. Venus is about the same size as Earth. Venus has an atmosphere like Earth. Venus is as far as planets go, at roughly the same distance to Earth, to the sun like Earth. So it's one of what we presume to be the most Earth-like planets. So there was a lot of interest in exploring Venus and trying to figure out how Venus developed and maybe correlating that how Earth might develop in the future. The problem with Venus, though, is that Venus has an incredibly dense atmosphere. So if you look at Venus through your telescope, all you see is this. All you see is clouds. So you can't see the surface with anything but radar. So radar was essential in the analysis and the studying of Venus. So when Magellan went up, in 1989, it was the first time that anybody had ever seen through the clouds of Venus over the entire planet. It was the first time that we got a map of what Venus is like underneath those clouds. There was a lot of stuff that they found. There's bunches of volcanoes, there are rift zones, there are huge areas, huge lava flows. And so it gave us a lot of insight into the history of Venus. And not only did they look at the surface itself, they also used images that were acquired from two different places. So they used one image that was acquired from here and another one that was acquired from here. And what you generate is a stereo view. It's like your two eyes, they're displaced, and through that you can see, you have depth perception, you can see three-dimensional. So they used images from different geometries to get three-dimensional data of Venus. So they also, actually, I'm very disappointed about this video. This is a 3D video, supposedly, but I'm not sure if you can actually see the 3D. This is one of the mountains, one of the volcanoes on Venus, and the whole three-dimensional shape of it was only known due to radar. And so nowadays, you can use this kind of information, and you can take other stuff that people had since found out, data from other sensors. You can drape them over the information you have from radar, and suddenly you can analyze all this data way better. You can understand its three-dimensional behavior, and it helps you way better understand the evolution of the planet. So with that, I essentially want to end. I want to bring up one last point why Venus is important for you. And 2.5 years ago, actually, the University of Alaska Fairbanks led an effort for a Venus mission. So there was, at the time, Vice Chancellor of Research, Buck Sharpton, had headlined a team that had UAF, Boeing, and MDA, and a bunch of NASA and so on in it, to build a new system that should go out to Venus and remap and reanalyze Venus, again using radar technology. And we got turned down at the time, I have to say, but who says? I mean, we are planning at least to resubmit that proposal in the next round, and maybe in the near future we can bring Venus to you, and maybe you can essentially own Venus. So with this slogan, dare mighty things and let radar guide your way, I end this talk, and I thank you for your attention. Thanks.